welcome to the course Advanced Reaction Engineering. So, in this course today we will discuss about catalyst characterization techniques, BET surface area, pore size and pore volume. So, in our previous class we already have discussed about the catalyst. So, how the catalyst we can synthesize, and once we conduct any reactions, then the catalyst you have to put inside of that reactor. So, then once it is maintain a particular temperatures and pressure for that particular reaction. So, then we will get corresponding product at a particular selectivity or yield that we can get. So, catalyst is very important components for any reaction engineering catalyst or reactor study. So, catalyst a very small amount of the substance that usually we put inside of a catalyst, that may be solid form, liquid or gas forms. It is in the form of metal oxides or enzymes. So, that actually changes the rate of the reactions. So, then if you let us say for a particular reactions, here A is A plus B going to C plus D, that is the product, and here this is the reactant. So, here we can conduct this reaction by considering catalyst 1, catalyst 2, catalyst 3. 3 different catalysts we have synthesized, and 3 catalysts we can use for this particular reactions, and all catalysts are active for this particular reactions, let us say. So, but in case of catalyst A, it requires low activation energy as compared to the catalyst 2, and catalyst 3 required higher activation energy to conduct the reactions. So, here why one catalyst required low activation energy, another catalyst required high activation energy, means that we need to know, means therefore that is actually means whenever the catalyst you have synthesized, similar material or same components maybe we have used, but the properties when we are checking in terms of conversion, yield, selectivity, then we check that the one catalyst performing better compared to the other catalyst. So, that means we have to know the catalyst characterization. So, therefore, that is the catalyst characterization, that is why it is important. So, maybe this is catalyst 1. If we go very details in depth of this catalyst, all catalysts are in powder forms, its look maybe different colors or maybe different compositions are there. But once we go inside of that catalyst, let us say for this catalyst 1 it is spherical in shape, the crystal or crystallite size or atomic size, active sites. In this catalyst let us say it is cylindrical shapes, and for catalyst 3 it is maybe cubical shapes or that type of shape formation is there, that crystal arrangements or inside of the catalyst where the active sites are there. So, this way we can say just for get an idea about the catalyst. So, why one catalyst behave different or better than other catalyst. So, once we conducting these reactions, so we have observed that when we catalyst made the spherical crystallite size or particle size is spherical like this. So, then conversions we are getting highest, and when it is like this cylindrical shape, maybe we are getting highest selectivity, and this type of catalyst we are getting highest yield of these products maybe. So, means one catalyst behaving one particular way, so compared to the other catalyst. So, that is why when we choose a particular catalyst for a particular reaction, so then so many things we have to means cost of the catalyst, activity of the catalyst, performance of the catalyst, many things we have to, and stability of the catalyst, many things we have to check. So, here so when we choose a catalyst, so these are the things, means porosity of the catalyst, pore volume, surface area, whether the catalyst is amorphous in nature or crystalline in nature, so that will check. Acidity or basicity, means basic nature or acidic nature of the properties of that catalyst, the metals we have synthesized or the catalyst we have synthesized. Thermal stability, means if we prepared a catalyst and for a particular reactions, but reactions let us say it may be 200 degrees centigrade for a particular reactions, or any reactions it may be 800 degrees centigrade. At this temperatures we have to conduct the reactions. So, if we prepare the catalyst, it does not stable at 800 degrees centigrade, then we cannot use that catalyst for this particular reactions. So, and catalyst if it is stable low temperature, then you can use for these reactions, but not these reactions. So, that is why you means catalyst thermal stability is also important. Redox properties also we need to know, means oxidation states, electronic properties, that also we need to know whenever we are going to prepare a catalyst. At the same time, surface morphology means that also we need to know, means which particular means surface characteristics giving more sides or giving more activity. Elements presents means whenever we are preparing a catalyst, so many metals we are using to synthesize that catalyst. So, surface core, whenever the catalyst is taking part in the reactions, active sites is important. So, active sites means the elements that is present at the surface inside of that catalyst or the core. So, how they are distributed and what are the elements are present, so that is also important. Apart from that, the vibrational characteristics of the materials, particle shape, size, that are also important. So, that also we need to know. So, then once we compare and synthesize and suggest a catalyst for a particular reactions. So, characteristic catalyst means properties evaluation, that is very important. So, whenever we conduct a reaction, so then we need a reactors. Let us say this is a reactor packed with reactors. Here we placed catalyst and here's reactant molecules that would pass and we will get product C plus D here. So, here this is catalyst bed, here we are maintaining particular temperature pressure. So, here the components that we need to know whenever we conduct a reactions or carry out a reactions in a catalyst. So, number 1 is that reactions that we have to fixed, number 2 is the catalyst and number 3 is the reactor. So, these are the 3 components we need to know. So, reactor part already you have discussed, and reactions, let us say this is the reactions. Once we conduct the reactions, then at the end of the or exit of the reactors, so we will get the product C, D and unreacted reactants also will be there present. So, you have to analyze, means how much mole in terms of concentrations of A, concentration of B, concentration of C and concentration of D, these are the components needs. So, for that we have to need some technical, means analytical techniques, so by which we can measure the individual concentration at the exit of the reactors it is present. So, how much concentrations you have started with this, and at the beginning Ca and Cb, Cb naughts initial concentration we know, final concentration we need to know, based on that percent conversions, percent yield, percent selectivity. So, these are the things we can evaluate. So, for that we have to use gas chromatography, that is called GC, GCMS. Also we have to use if we have a liquid product and it is made of liquid mixture of more than one component. So, then with the help of GCMS gas chromatography with mass spectroscopy we can evaluate that quantify or quantity or concentrations which particular components at what percentage are present, that we can evaluate, okay, or HPLC also we can study. This is for reactions to reactant components, means evaluations or performance or means concentration evaluations. And when the catalyst is there, for that catalyst we need to know, means if you want to characterize, there are so many characterization techniques are available. So, out of that few characterization techniques we will discuss. So, all are not possible to discuss. So, today we will discuss basically BT surface area, pore size and pore volume measurements, that we will discuss. So, here is the characterization technique or catalyst characterization technique, we can classify that way. For separation technique this, and microscopic properties or surface morphology eliminations to find out, same term we can use. And for structural analysis, that is the BT surface area, pore size, pore volume, XRD analysis that we can do. And thermal analysis means TGA, thermogravimetric analysis, temperature program desorptions, temperature program reductions, that we can do. And few spectroscopic techniques are available, the UV NIR spectroscopy, FTIR spectroscopy, Raman spectroscopy, these are the techniques we can use as per requirement or as per availability. So, that we can use to characterize our catalyst or the materials we have prepared for our reactions. Okay. So, first we will discuss BET surface area analysis. So, in this particular means let us say this is our catalyst. I said that catalyst has so many pores. This is the catalyst spherical particles we are considering. Here this is the macro pores, this is the micro pores, and this is mesopores. This is micropore, this is mesopores are present. So, the different diameters of that pores that is present or exist in a catalyst, porous catalyst. So, maybe this type of categories we can classify it, and inside of that pores, outside of the pores. So, these are the active sites, so that are present. So, in the catalyst. So, now in the surface area means catalyst that we have prepared, that is in the form of let us say powder forms, very small particles. So, we cannot hold each particles and we cannot measure it if particle is very small. So, its dimensions means radius we cannot measure, diameters we cannot measure, its volumes to measurements is very difficult. So, if it is let us say like this type of object, so a regular object, and with the help of the scale we can measure the A side let us say 1 centimeters, this side is 1 centimeters, and this side is also is 1 centimeter for cube, and spherical spherical object, that sphere of that object we can know the radius let us say 5 centimeters, and its radius equals to 2 centimeters and length equals to 10 centimeters. So, then this type of regular object when we have, so easily we can measure the surface area, pore volume, everything we can measure, but when that material is like this powder, so it is very difficult to measure individual component surface area, volume. So, therefore, to measure those type of materials or components we have catalyst. So, BET surface area or the theory was developed and based on that, so we can say this theory, and this is the extension of Langmuir theory. So, Langmuir theory that was developed. So, that was based on Cambridge options and Fiji options, and after that BET theory that was developed for multi-layer Fiji options analysis. So, based on that the theory was developed. So, for that means with this means theory or this BET surface area measurements, some one equations is there and some experiment is there. So, with that helps this type of particles or surface or materials is there, means not regular material or surface. So, irregular object. So, in that case surface area we can find out, pore size we can find out, pore volume also we can find out. So, these are the things easily we can find out with the help of these techniques or BET surface area analysis. So, here is the experimental setup or equipments that we need help of that. So, with that equipments, help of these equipments we can easily find out BET surface area. So, here nitrogen gas we have to use for adsorbing molecules. If we have let us say surface. So, in this catalyst surface here nitrogen molecule get adsorbs over there, and then so how much molecules if we maintain particular temperature, let us say 77 kelvins we are maintaining, and so we are passing nitrogen gas at this particular temperature will adsorb over the surface, and that adsorption is Fiji options. So, there is no chemical bond. So, Fiji options is there, and layer means adsorption should be there over the surface of that catalyst, pores everywhere. So, then if we increase the pressures, then more and more nitrogen molecules get adsorbed over the surface. So, then like this type of isotherms will get. So, this is adsorbs volumes, experimentally we can measure the amount of nitrogen get adsorbs in terms of centimeter cube per gram, and then this type of isotherms will get. This is adsorptions isotherms for adsorptions, and by here x axis with increasing relative pressure P by P naught. P naught is let us say 1 atmospheric pressure and P is P by P naught. So, P by P naught, so that is the relative pressures. If you increase the pressure from left to right, so the curves would look like this, and so one adsorption is over, then we dissolve that gas whatever it was absorbed. So, it would take out or come out from that surface, then the nature of curves would be like this. This is desorption curves, desorption isotherms, and this is adsorption isotherms. So, it would be look like that. So, experimentally these are the things we can quantify, means how much quantity of nitrogen get adsorbed and how much that is desorbed when desorption was carried out experimentally with the help of these equipments. So, now this is the BET equations. These BET equations here detailed derivations I am not discussing here due to the time constraint. So, here directly we are discussing this equation. So, with the help of these equations, if you are know this is relative pressure P by P naught, P by P naught is the relative pressures and Vm is the monolayer formations, monolayer volumes. So, if this surface is like this, here's molecules get adsorbed and one monolayer coverage is there. So, this is Vm. So, total surface it is covered by nitrogen molecules. So, if you are able to find out, so that is monolayer volume is called. So, if it is completely adsorbed, then complete monolayer formations is there. If it is partially fill up, so then not monolayer. Adsorptions may be like this is not complete, this is complete, but this is not complete. So, these are the empty spaces are there where nitrile molecule does not get adsorbed. So, this is not monolayer, so this is monolayer formations is there. So, here's means experimentally when we increasing the pressure, let us say one example I am taking for a particular catalyst. So, this amount of the volumes of that nitrogen molecules get adsorbed. So, here if we increase, see pressures of nitrogen that was 10, 20, 40, 100, 150, 200 like that 500 millimeter per mercury, if we increase the pressure, then that volumes of nitrogen get adsorbed, that gradually increase, that way it is linearly or maybe that depends upon that materials it is showing like this. So, if we have these equations we can find out how much quantity of gas get adsorbed, and from that BET surface area easily we can find out. So, that we will discuss, and there is means pore size and pore volumes also we can measure, but by using BHG method and here this equations is there. So, means ln P by P naught, that is the relative pressures, and gamma is the surface tension, R is the gas constants, and Rp is the pore radius, and T is the thickness of the films adsorbed on the pore surface, and Vm is the molar volumes of nitrogen at 77 kelvins is this. So, this equation is taken from this means here we can get it. So, means this is Kelvin equations, with the help of that. So, that pore radius we can find out, Rp we can find out, and pore volumes also find out using these equations. Here if monolayer volumes if it is known, and G is the how much quantity of gas get adsorbed during experiments. So, with that helps, so average pore volumes we can find out. Okay. So, now with the help of the experiments or these experimental setups, the materials, let us say here so many catalysts I am taken. So, from these articles we have taken this. So, here these are the catalysts they have taken, the BET surface area, pore size and pore volumes it is reported. So, in this catalyst you can see the surface area is 4 meter square per gram, and pore size was 239 angstroms, and pore volume is 0.04. So, when this was the bulk catalyst, when support was used to make that catalyst supported catalyst, same catalyst, but here support was used. So, here you can see surface area was increased 4 to let us say 145, so meter square per gram. So, by using surface means surface area increased, and at the same time pore size and pore volumes also it is changes from one materials to another materials. So, these are the materials here in you can also see that. So, here also means one materials to another material, surface area is different, pore size is different, pore volumes also different. So, each catalyst showing a different experimental results. So, these are the things we can get from this means studies. So, in these studies the isotherms I said, means this is called isotherms or BET isotherms, like that one materials to another materials, if we do the same experiments, means adsorptions isotherms, desorptions isotherms if we conducts, the nature of these curves would be different from materials to materials. Okay. So, why this type of isotherms is come? So, here type 2 and type 4 isotherms. So, there are type 1, type 3 also, type 5, type 6 are also there isotherms, that I am not discussing. So, only type 2 and type 4 I am going to discuss. This is type 2 isotherms and this is type 4 isotherm. So, in type 4 means here's adsorptions and desorptions it is following like this the same way. So, here's means in this particular isotherms that also based on some BT multilayer physics based on that this type of isotherm also developed, and this type of isotherms also, but depending upon that materials or nature of that surface. So, here's adsorptions lines was following the blue lines and desorptions lines or curves is following this desorptions and this is adsorptions. So, this and this two different material, not the same material. This is material particular type 1 and this is type particular type 2 let us say. So, two different natures it is showing. So, here's means what kind of means the significance of this particular curve. So, here first type 2 isotherms I am discussing. So, since we have taken say materials and there's it may be pores are there, this is pores you can say. So, this blue lines is the pores. So, pore is available. So, hence this is relative pressure. So, P by P naught is this and this is molecules get adsorbs volume in terms of centimeter cube nitrogen per gram get adsorbs. So, from here we have started here. So, if we gradually increase, so means from here to here if we go. So, here you can see unsaturated binding means pore is there, red dots this is nitrogen molecules, this is nitrogen molecules. Okay. So, nitrogen molecules means get adsorbed over the surface, but the adsorption is not complete. So, here when pressure is this, when pressures if we gradually moves increase, so then it would become here means here. So, monolayers or this surface all covered by this saturated monolayer bindings means all the surface occupied by the nitrogen molecules. So, then it becomes saturated monolayer is from here. So, after that if we further increase the pressures, so then the curves would be like this means monolayer to multilayer shifting, multilayer adsorption. So, up to this monolayer and saturated monolayer, after that if we further increase the nitrogen pressures over the surface of that catalyst or materials, the pores available with that multiple pore formation would be filled up by or multilayer. This is layer 1, this is layer 2, this is layer 3. Once layer 2, this is layer 3, but multilayer adsorption is there and here's phase separation is there, and after that if we further increase the pressure then it would be saturated and capillary condensation should be there. So, after that, so this is adsorption curves or this adsorption isotherms. So, we can see that. So, like this it is happens means when nitrogen molecules pressures we gradually increase over the surface of the catalyst. If we increase the pressures or relative pressures of the nitrogen, then the amount get adsorbed gradually increase and it would be like this. So, here I said it actually indicates so monolayer adsorptions in micropores fillings up to this, and once it is saturated then mesopore filling has started. These are the actually mesopores. So, mesopores of the molecules gets adsorbed, this is micropores fillings and then mesopores will fills and then here mesopore completely fills at this particular points, and after that if we go then straight lines or flat will reach, that is means capillary condensations would be there. So, means liquid here completely filled means the pores is available in the surface of the catalyst, it is completely filled after formations monolayer multilayer. So, multilayer formations. So, all pores are occupied by the nitrogen molecules, and again if we further increase the pressure then liquid like state will forms and capillary condensations you can see at this particular states. Okay. This is type 4 isotherms. Okay. So, now numerical examples will get means study. So, there we will find the monolayer volume specific surface area of the catalyst meter square per gram. Means if we conduct the experiments from the adsorption isotherms, this is set 1, 2, 3, 4, 5, 6 multiple points were taken. So, when pressure was this millimeter mercury then centimeter cube of nitrogen get adsorbed is this for this amount of the catalyst. So, when partial pressure is this that So, this way if you increase the partial pressures, the amount of the gas gradually a volume of the gas nitrogen gas get adsorbed from the experimental data for a particular catalyst is showing here. So, here catalyst was taken 0.1 gram, total surface area we can find out St, that is equals to Vm n S by V, and specific surface area that we can express in terms of S and equals to St by A. St is the total surface area. If we divided total surface area with respect to the amount of the catalyst, A is the amount of the catalyst, St is the total surface area, then we will get meter square per gram of the catalyst. So, this is for 0.1 gram of catalyst. So, here catalyst was this. So, total surface area will get, and then specific surface area per unit mass we can find out this way. Here total surface area if you want to calculate, then we need Vm, that is the monolayer volume, this is n numbers, and S is the okay. So, here S is that cross sections area, actually here this is different. So, here cross sections area, this area cross sections area of nitrogen, actually this is different, this is cross sections area of nitrogen. So, now we have these equations and we have these tables. So, from these tables how we can calculate specific surface area. So, here means these are the data we have experimentally obtained. So, then P naught equals to this millimeter mercury, 760 milliliter mercury. So, we can calculate P by P naught. So, P is there, P naught equals to 50 by 760. So, like that we can find out this, and after that we can find out this. So, we know P naught is known, P is known, V is known. So, using this we can find out. So, now P by V into P naught minus P against P by P naught. So, as per BT surface area equation, this we have to develop and this we have developed. So, this and this we have to plot in the graph. In the graphs, this is y axis and this is x axis. We are plotting this against P by P naught. So, this is y axis, this is x axis. If we do plot, so it would be like this. Okay. So, that type of equations or these lines represent this. From here slope and intercept we can find out, intercept and slope we can find out. So, some numerical value will come. So, let us say from that slope we are getting, that is S equals to 0.1 and intercept is this. So, from the slope and intercept we can find out Vm. So, this is slope and this is intercept. So, from slope and intercept we can find out Vm, that is the monolayer volume 9.48 centimeter cube. So, that we found out. So, we from that graph Vm we know, N is this and S is the cross sections area here. This cross sections area, instead of S we can write PS. PS means nitrogen cross sections area of nitrogen molecules equals to 0.162 nanometer square equals to this centimeter square per molecules at 77 Kelvin. So, these are the components we know. So, now V is also known, V is the molar volumes of nitrogen is known. So, then St we can find out. So, St value that would be known. Once St is known, so that we can substitute here, A is known. So, then specific surface area we can find out. So, St first we have to find out. So, St we have found by considering Vm, that we have substituted N equals to this specific one nitrogen molecules having surface area this, molar volume of nitrogen at 77 Kelvin is this, then total surface area equals to this, and specific surface area we can find out divided by the amount of catalyst was taken. So, then the total surface area and after that specific surface area per unit mass of the catalyst we can find out. So, then average pore volumes also we can find out. So, once we know molar volumes that we have means from that these equations Vm we have calculated 9.48. So, 9.48 we can substitute here. Okay. So, the Vg, the amount of the gas adsorbs, the total volume 0.1 gram of catalyst absorbed that much volumes gas of nitrogen. So, then Vg equals to this. So, that Vg we can put it here and molar volumes of nitrogen is this. molar volume, this is molar volumes, and Vg is the amount of the gas get adsorbs. So, then total average pore volumes we can find out. So, if you substitute this, so then average pore volumes we can find out by using these equations. So, pore radius also we can find out by using Kelvin equations. I said using this equation, thickness of the film adsorbs, this thickness we can find out, this is the thickness. So, means 1 molecules of forms 1 adsorb film, that thickness is this, and rest of that part is 2 into Rk, that is condensed liquid. So, condensed liquid, so Rp equals to Rk plus T, Rp is the pore radius, Rk is the Kelvin radius or condensation occurs, and this is monolayer. So, here's the details of these equations you can find it here. So, from there we have taken and we have calculated first for a let us say P by P naught equal to when this. So, at this particular pressure, so we can using these equations we can find out, put P by P naught is this minus 2, this is means surface tension of the liquid boiling points at of nitrogen, surface tension of nitrogen at its boiling point is this, and molar volumes is this, R and temperatures we know. So, then Rp minus T we can calculate by putting at this particular pressures. So, then T can calculate by using these equations. So, here P by P naught if we put, so T will come this. So, then if we substitute T here, so then Rp we can find out, that is the pore radius or average pore radius, you can say 27.74 nanometers. So, these equations we can use. Okay. So, this way, so we can means from the experiments, this data we have means pressures against the volume get adsorbs, these tables we know, and we have these equations, with these equations, and we can find out the surface area by plotting. So, once we do the plot this versus this, and from this intercept and slope we can find out, and with the help of intercept and slope we can find out the monolayer volume, this is the Vm. So, Vm we can find out, and once we know the Vm, so then we can find out total surface area, and once we know the total surface area, so specific surface area per unit gram of the catalyst we can find out. Similarly, we can find out average pore volume and average pore radius also we can find out. Okay. So, today is up to this. Thank you.